Going through Flare Data Connector, specifically a practical session, and we covered a number of things in the previous session. So today we'll be seeing how it actually works practically. But before we start, I'm sharing a link to the Riser pad in the chat here. So please make sure you check out the links that we're going to be covering today, but there's also a link to the feedback form. Anything you've learned today or anything you think you should communicate about today's session, you fill it on that form. I think I should share my screen to that form so we can all see it. So this is the form. This was information from the previous session, and you can find the information for today's session right here. The feedback form is there, and please put your name and X handle here so that we can be in touch. And then the links are down here, but I'll keep populating that list as we keep going. And yeah, I think we can get into the session then. So today we'll be looking at Flare Data Connector more practically, but I just want to again go slightly over an overview from the previous session so that we could refresh our minds about it. So like we said the other time, it's Flare's cross-chain protocol, and also the protocol that fetches Web2 data. And as you can see here, there's a depiction of the different sources this data can come from. So it could be data from Bitcoin, from Doji, from Ripple, or they put in the X handle here, rather the X logo here, but simply to represent Web2 data. So all those different sources is where the data that Flare Data Connector brings on chain. And like we said, when the data is supposed to be brought on chain, it has to go through a verification process, which involves all the data providers. In this case, they will be working as the attesters of this data to verify if actually that data is authentic or it actually exists. So each of them would make a GET request to that to those different data sources, and then come back with the data, and they check against each other to see if the data is actually consistent for all the validators. Then, yeah, when that is done, a Merkle tree is created for the data that has been verified. Then the Merkle root is generated and put on chain, and you can access that data through the data availability layer. So essentially, that's what happens here. The verifier reads the data, and then they go through a voting process to verify the authenticity of that data, and that happens in a period of about 90 seconds, although it could go slightly higher, for a number of factors. But then after that is done, your data is now available for you to use in your smart contracts. All you have to do is just verify the data and the proof that was generated by the FDC protocol, and then you can have your data accessible to you through your smart contracts. So yeah, this is just another depiction of the sources of this data. So currently, Flare Data Connector is active on the Flare network. So that means you can get data from Songbird or from the Flare networks themselves. That is mainnet, Flare mainnet, and Flare testnet. Flare testnet Coston 2, then Flare testnet Coston, and then Flare Songbird network. Then we have XRP and Bitcoin and Doji and Ethereum, and then Web2 data. So by the way, for all these chains, both their mainnets and testnets are actual sources of this data. So even on Ethereum, Sepolia itself is also a source of this data. And the Web2 data, of course, that means you can query any API and verify that data and bring it on chain. So today we're going to actually be doing a Web2 JSON query, and it's the data that we're going to be bringing on chain. And this is the workflow. So we're going to be following this workflow as we bring this data, as we try to go through the attestation process of the data that we're going to provide. So the very first step, as you can see, is to identify the transaction. Then you prepare an attestation request, then submit the attestation request, and then extract those the proof and data that have been delivered to the DA layer. And when you verify it, you can use that data on chain then. So yeah, that's pretty much it. This is a workflow that we actually looked at in the previous session. So as a user, you would observe data, then prepare an attestation request to the verifier server, and from there, then you send a request, an attestation request to the FDC protocol. And when it's done, when the round is finalized, you can pick both the test and the data through the DA layer and provide it to your smart contracts. First, to verify the data, to verify that this data has gone through the attestation process. So the macro proofs that are provided by the DA layer should also be verifiable against the macro root that is provided on chain. And then when the proof is successful, then you can access that data and use it. And yeah, this is just a repetition of the exact thing we've been looking at. So I think now we can go into a practical session, and we're going to be following this workflow. So the very first thing we're going to do is identify the transaction. But for the data that we're going to use, I'm going to share a GitHub repository that is on the Flare Africa GitHub account. So we're going to be following that example and providing that data on chain. So the link is here, and you can find it in the RiseUp pad. You already have the link to the RiseUp pad. So this is the data that we'll be bringing. I'm just going to clone this repository, and we'll be working with this repository. It's derived from the hard starter kit for FDC of all the different attestation types. So like we talked about it the other time, the different attestation types that you can request for verification from. It could be an EVM transaction, it could be Web2 data like we're going to do today. But this FDC repository is specifically contains information just for attestation of Web2 data. So I'm going to clone it, and then we're going to use this one. Okay, I hope my screen is visible. My command line. Okay, let me put it on a desktop. Call it Web2 JSON. Okay, so this would be, no, I will clone it here. And then all the information that we really need regarding this attestation request we're going to make, some of it is within this GitHub repository. That's why I wanted to clone it first, so that I can demonstrate, I can show you some of the things that we'll be requiring to use for us to make the attestation and then be able to access this data on chain. All right, so this is actually the repository, and I will, let me see where to go first. So I'll first go to the script that we're going to be looking at later on for us to be able to make this request successfully. So first of all, the very first step says we need to identify the transaction. So that was specifically for the EVM transaction standard, but rather the EVM transaction attestation type, but it is really just the first step. Identify the kind of data. It really means that represents identifying the data that you're going to be bringing on chain. So first of all, you must know where this data is, and you must be able to probably even access it yourself before you can put it through the FDC protocol. So that's what we're going to do. And the endpoint to the data that we're going to be bringing on chain is right here, this API URL. Let me increase the size of this. So this is the data that we're going to be bringing on chain. It's retrievable at this endpoint, at this API endpoint. So I want us to first be able to see this data ourselves, because this is just the link to the data, it's not the data itself. So I want us to first look at the data and then we shall be able to see how the process actually goes from here. So I'm going to use an API service, Postman. If you've been building backend services or some applications that require working with Postman, I'm sure you're familiar with it. So it's what we're going to be using. We're going to just make a GET request to see how exactly this data looks like. And then we can see the process through which it was taken for it to be delivered on chain. So this is in the script of the repository I just brought from GitHub. So as we're looking at this data, I am going to install the packages that I need for me to be able to operate and maybe run scripts from this repository, this application. FDC. Yeah, so I'll install install. Okay, so it will be installing the packages we need as we look at the data. So from here, I just want to copy this link. So I just want to query this data from this API endpoint to see what it actually looks like ourselves, to see what it looks like before we can take it through the FDC protocol. This is a standard mechanism for which data can be brought to any platform. But you can imagine it has to go through an entire verification process for it to qualify to be on chain, particularly on the Flare network. You'd imagine, why can't I just get this data from here, right here, and then put it in my smart contracts in just a simple front end write contract method, operation, or transaction. But the issue is we cannot guarantee the security or the integrity of this data. At sometimes you might receive it here and it shows you something, and then at the point where you actually provide it to your smart contract, it reads something else. And since it's only one point of failure, that it's only you that is getting this data and no other person can verify the integrity of this data, there's you're vulnerable to a number of attacks, you're vulnerable to a number of security breaches. And that is why FDC is important, because when an individual is providing data, or maybe if this API endpoint is providing illegitimate data, unintegral data to standard that FDC requires, then it can be rejected and the verification doesn't happen for that data. Or if perhaps if the different attesters are trying to verify if this data is exactly the same, but it generates different results every time they query that endpoint, then the verification will not happen. So it secures you from using data that is probably compromised. But if you're using a Web2 API endpoint and just sending that data to your smart contracts through perhaps your decentralized application directly without going through a verification process, there's a likelihood you could already be compromised and you're vulnerable to a number of attacks. So that's why FDC is important. Yeah, so I'm going to put my endpoint here and then send a request to this API, see what the response is. So we can see this data ourselves before we take it through the verification process. Okay, the request was successful. I'm just waiting to see the response body, the response object. Oh, it's right there. So as we can see, there's a JSON object that has been returned. So it has a name, has a height, has a mass, has a hair, has a number of properties. So as you can see, this is data that has come from that endpoint. And that's exactly what would happen when we make the request here. So this is exactly what the different attesters would do. They would go to this endpoint and derive this data. Then maybe check against each other to see if validator A picked exactly the same results as the second validator, or the third validator, or the fourth validator. And then when they can verify that each of them have exactly the same data, the consistency is 100% for all the different queries to this endpoint, then they can sign and verify that this data is actually integral and can actually be used on chain. But something else happened with this specific request. There was a JQ filter. So a JQ filter is like is a mechanism by which a JSON object can be filtered, like maybe pick out certain properties and restructure the JSON object. So in this case, the JQ filter is right here. So this request picked out the name, picked out the height, picked out the mass, picked out the number of films, and then got the length of the array of films, and all these other things. It's really just about filtering the returned object. So that is not, it's not the entire data set as it was brought back from the endpoint. As you can see here, the data object is really, really big, has a number of things, and some of them are not really considered to be into the final object that is returned on chain, that is returned by the attesters. So the attesters have to actually apply the JQ filter to the data that they've fetched as well. And that's part of the request that we're going to make, the request that they make rather. So yeah, the rest of this is more information about the request itself. So I won't be doing a lot of actual coding because there's a lot of things to review for us to understand how FDC works. But maybe I'll record a session later where I go through these things step by step, perhaps redoing them for a different API endpoint. But this should be more than enough for us to understand how it actually works and how to prepare the requests and the attestation and pick the data and proof from the data availability there. So yeah, that's this is really it about preparing the data. So going forward, there's a number of functions in this script, and I want us to look at them one by one for us to understand how it actually works. So like we said, when the data is delivered on chain, it's delivered as a structure, and we'll also look at that. So there are a number of functions that correspond to the different steps in the process of getting this data on chain. So we've already identified data that we want to use. So what is the second step? The second step is prepare an attestation request. So an attestation request, like we saw with the Swagger UI the other time, it was failing because I was doing something slightly wrong. I was encoding a certain component slightly wrong in the previous session. But preparing an attestation request, maybe I could do it here still for one of the different attestation types so that we could at least see what it looks like. And it's exactly the same thing we're going to be doing in a script. So let me prepare one for an EVM transaction, because this is the kind of data that you're now going to pass to the FDC hub contract. So the FDC hub contract is the entry point into the FDC protocol. It receives that data, it initiates the FDC attestation process, and you can actually verify that the process is actually happening, as we're going to see. So this is the interface for the API endpoints of the verifier server. So if you want to prepare an attestation request, you can do it through this UI. So for you to prepare an attestation request, you must know what endpoint calls specifically. So there's a number of endpoints here for different attestation types. For address availability, it's over there. For balance decreasing transactions, and from here you can see the URL type that it's actually for the XRP chain, but I'm looking for the one of Ethereum chains. It actually has the oh, this one is for XRP. So I'll go to the default. Let me share the link to the verifier server as well. I'm going to put all the links on the riser pad. So if you want to go to these different links, you can always just come to the riser pad. It will be available even after the session. So you can come to the riser pad and you'll be able to get all the data. So yeah, so I'm right now on the Ethereum, on the EVM transaction API. So there's a number of EVM transactions here. There are those for ETH, there are those for Flare, there are those for Songbird. So you need to be careful where you're going to actually make the request from. When I click prepare request, it will open this part and I can try the endpoint out. The only restriction to this is that I have to provide an API key, and it's just a bunch of zeros, but you have to provide them for you to access that API. And everything regarding accessibility is right here in the example.env file. So I'm going to take this API key. It's the one that I will use, and I put it up here. Authorize myself to use this API. I'm authorized now to use the API. So when I make a request here, so I specify the attestation type. So these are just byte 32 equivalents of the actual words representing these different requests. So this attestation type is a byte 32 encoded equivalent of this actual word EVM transaction. And then the source ID, it's also a byte 32. It simply represents the keyword test if, which represents the network that we're actually going to be making the request to. In this case, it's Sepolia, Ethereum Sepolia. So I'm going to put the source ID here. Let me first try to make an execution. I don't want to wander around trying to find them. So this will fail because this is not the correct source ID. This is also not the correct attestation type, but it will, oh, I'm unauthorized. Thought I was authorized. Okay, so I'm authorized, hopefully. When I execute, this is going to fail. And yes, it says attestation type and source ID combination are not supported. So the correct ones are these, EVM transaction, and then this for test ETH. So I have to copy this. And after I copy this, this should generate for us the correct request that we can then send to the verifier server. Then this represents test ETH. Okay, so now I have to get a transaction hash of a transaction that already exists. Since this is failing, I'm going to use block scout. So I'm just left with this, and then I should be able to make the request successfully. Then after I've showed us how the ABI encoded request looks like, then we should be able to move forward to the next step in our script. So the request has a number of parameters. It has an attestation type, the source ID, the request body, the transaction hash, the required confirmations. And this is specifically for an EVM transaction. So if you're making a Web2 JSON request, we're going to see it actually looks different, and we'll be able to identify the different parameters that we can then enter into the request for us to be able to get this data brought on chain. Okay, just a moment. After we get a transaction hash, we should be able to prepare a request for an EVM transaction. I'm doing this just for us to see how it actually looks like. So I want to get, okay, there's a token transfer here. This is good enough. Yes, if I get the transaction details, transaction hash, this is all I need. So now I put the transaction hash right here and execute. I should be able to get invalid. I kept getting this error. I have no idea why. I hope I didn't miss out a thing. Yeah, sure I didn't. I interleaved this section of the video to highlight an inconsistency. I don't know why it keeps failing, but there's a bit of an inconsistency. So everything else is the same. I've only changed this transaction hash, and I require that it has at least 2 required confirmations. And when I execute this, it does return a valid ABI encoded request. And as you can see, it has an attestation type as the very first component here. So it's just a concatenated hex string of all the elements in the request body. So we have the attestation type here, we have the source ID 074. It is right here. So these are all 64 character padded hex strings just put together. So this is up to 64 characters, which makes it 32 bytes. These two, exactly the same thing. As you can see, it ends about somewhere there. And then we have the transaction hash slightly below 0x4e, 4e. So we have a 4e63 here. That's the transaction hash. Then in the middle here, we have the message integrity checks, just a checksum for the entire data set, the request rather, to help validate if the request is still integral with the data that it represents. And I'm going to change this transaction hash to represent a transaction to prepare a request for a transaction that is not this one. This is the default transaction in the EVM transaction request hard component. So I want to change this transaction hash into a different transaction hash that I've derived from Block Scout. And as you can see, it already has 4 block confirmations. And my requirement, my stipulation in the request was 2 block requirements. So it should work. Ideally, it should work because I'm only changing the transaction hash. And that's a valid transaction hash. When I click execute, down here it reads that this is an invalid request. The response body is invalid. So I don't know why this happens. Probably need to figure it out, to maybe ask the people that design the API why there's this kind of inconsistency. But in case you land into it, it might not be exactly that you wrongly encoded the message, the request message. You could just continue and do it with a script and prepare the attestation request with a script. All right. Okay, we have all our data and we have applied a jQuery to it in our script. So this is the request that we're going to be giving to the attesters for them to be able to make the request successfully, to verify this data for us. So the second step rather, is for us to prepare an attestation request. And since we're doing a Web2 request, a Web2 JSON request, this is how the request body looks like. You provide the URL and the method that you're making. So it's a GET request in this case. The headers that you need, if perhaps there's a specific data format with which this data is produced, you need to specify it. Or if there's an API key required for you to access this data, you put everything like that in the headers. Then if you have any query parameters or anything in the body, you put everything there. Then the post-process JQ filter rather. So this is applied after the data has actually been fetched. Then the ABI signature. And everything is right up here. So I shared the link to this repository, so you should be able to review all these things. Then this is the link to the verifier server that prepares Web2 JSON requests, and then the API key right here. So you get all this information and pass it on to the prepare attestation request base. So this is just how it was designed in this specific repo, but we can always rearrange it in any way that we want. But I'll follow this this standard for now because it's much easier for us to reapply. But if you want something that is also very detailed and covers all these things to the foundation, I could do that as well. So when this data is obtained, it's sent to this other method, which is where the actual process happened. The actual attestation request happens. So you can see the attestation types and source ID are turned into their hex equivalents. Then down here, after everything has been prepared, after the entire component of the request body has been prepared, the request is then sent to the verifier server. So this is the URL of the verifier server. When you go up here, we should be able to see it. This is the URL, and this represents the endpoint to the verifier server, where we can return a request body of the ABI encoded request that we can give to the FDC hub contract then. So after we prepare this data, we make the request to the verifier server, passing in the API key and the type of the objects of the data that we're passing in the body. It's a JSON object, so we pass in and the response comes back. And when we get the response, we already have the ABI encoded request that we can give to the verifier server, rather to the FDC hub contract after this function executes. That's the purpose of that function. And as you can see, this function was actually wrapped inside this other function, prepare attestation request. So the entire process happens in this function, but since it returns promises, it has to be awaited. And this is what happens next. So you send that message to the FDC hub contract. So there are other methods in here that refer to certain things required. Yeah, they refer to certain things required in the process of getting this data. You can calculate the round in which the attestation is going to happen. So there's a method here that is specifically just calculating the round. And you can see the code base is really big. That's the reason why I'm not going to be actually typing and writing the code. But maybe later on I could do a session where I cover all these different parts in detail and how to regenerate them or maybe rearrange them. But this template is just perfect for Web2 data. If you want to bring Web2 data on chain, it is the best template because it is removed from the entire hard starter kit that has all the different attestation types and how to work around with them for you to deliver that data on chain. So maybe I'll prepare specific repositories for those other attestation types, because this is specifically for Web2 data. So you can calculate the round and then you submit the attestation request. So you need to get the FDC hub contract and then submit the request. And when the request is complete, so what you do is when you submit the request, all you have to do is just wait for the round to complete. So when the round completes, then you should be able to query that data from the DA layer, and you can actually watch the entire process happening on the Systems Explorer of Flare, like we're going to see. I'll show you. And yeah, here you can send a request to the DA layer. So when you retrieve the data and the proof from the DA layer right here, first you give it the ABI encoded request of the request that you sent to the FDC hub contract, and then the round in which that data was verified, and then the URL of the verifier server. So what happens is all these components now can point to a specific set of data that went through the attestation process in the FDC protocol. So after that, if you've verified that if this data and the proof and the macro proofs that were generated regarding this data are returned to you, then you can pass them into your contract. So that's the process at which, the step at which we are now. So we prepare the attestation, we submitted the attestation request. Now we're trying to extract the proof and the data from the DA layer. So for you to extract the proof and the data from the DA layer, you need to provide the verifier server link, then the ABI encoded request that was sent to the FDC hub contract, and then the round in which that data was verified, in which that data was attested. So this returns for you the data itself and the macro proofs regarding that batch that was verified. So maybe I didn't talk about, I think I talked about it in the previous session. So verification happens in a period of about 90 seconds, and all the requests that were provided within that period are batched together. The different requests that will actually go through the attestation process successfully are added to a macro tree. That data is added to a macro tree, and then a macro root is generated and brought on chain. So on Coston 2, where we're going to be deploying our smart contract, the macro root already exists after the round. So we provide the data and the proofs that we got from the DA layer to the smart contract to verify if actually this data was verified through the FDC protocol. And we test the macro proofs against the macro root that was generated. And when the proofing is successful, then you can access this data and use it in your smart contract. So we'll see that as we look at the smart contract end. So now we already have the data and the proofs. The next step will be to deploy and verify the smart contract that we want to use. And you don't exactly have to do this here. You could have done it somewhere else. You might be using this entire process for a smart contract that already exists. Here you'll be deploying and verifying your smart contract. And when that is done, then you can interact with the smart contract here. So you give it the data that was provided from the DA layer through this function, as you can see. And then you can actually interact with the smart contract. So specifically, our smart contract, the one that we're going to use in this example, has certain functions that I want to show you. The specific function that was interacted with during this example was add character. So what is happening in this case is that we're getting the data and then using the data to add a character to the state of this smart contract. Okay, so when we go back to the script and see which actual method was interacted with, so this is a decoded response, and then so character list in this case is an instance of the smart contract, and it was generated here. If you're familiar with hard hat, you must know. So when you compile your smart contracts with hard hat, they generate artifacts. So in this case, this is the compiled artifact that we're using. This is actually the artifact that was deployed, but then we're going to use an instance of this artifact to interact with the smart contract. It's almost like a combination of everything that you need to interact with the smart contract, including its ABI and bytecode and the metadata that you would require for you to interact with the smart contract. If you've worked with Solidity, I'm sure you've used sometimes smart contracts to deploy other smart contracts. So they generate an object called a typed reference, which has everything you need to interact with a child smart contract. So it is exactly the same thing that is happening here, only that it's happening off-chain. So as you can see here, we have the Web2 JSON verification artifact still, because there's a number of components that are required for you to successfully utilize FDC. So many other smart contracts that might be in the core of FDC itself or peripheral contracts to the FDC protocol, they're all required for you to utilize the FDC protocol. So after everything has happened, then we interact with the add character method here, and pay attention very carefully here, because this is the format of the data that is returned from the DA layer. All the different attestation types have the data returned in this form. So this usually represents the attestation type. So in this case, it's iWeb2JSON. If it was an EVM transaction, it would be iEVM transaction dot proof. But when you see the word proof in this case, it just doesn't represent the proof. And I want to show you how this object actually looks like, because it's very critical to how we're going to be able to destructure it later on. So if you want to see anything regarding the different interfaces, everything is available on the NPM package of the Flare networks. So when you come to the NPM registry, you should be able to see the structure of these different interfaces and how you can actually interact with them. So the one that we're actually interacting with in this case is iWeb2JSON. So that's the interface I want to look at, so that I show you how this data is actually delivered. Everything is under Coston 2 in this case, since we're going to be deploying on a Coston 2 test network. When I scroll down, I should be able to see iWeb2JSON dot so, and it is right here. So when I click on it, it will show me the interface, and you can see the form in which the data is returned is in this form, iweb2.json.proof. That's the form in which we get data from the DA layer, and it is right here. It is a structure inside an interface, so you access it with a dot notation. So it contains two things. It contains an array of the Markov proofs. So when you're trying to verify your data on chain in your smart contracts, when you pass this into the FDC verification interface or the FDC verification contract on chain, it will pick these Markov proofs, the ones that are returned in the data, and test them against the Markov tree for that specific data. Because there will always be a Markov tree rather a macro root for a specific set of data that has macro proofs for the FDC protocol. So you have this, then you have that data itself. Now this is the information that has actually been verified and is now available for you to use. And it's in the form of the response structure. So when you check the response structure, it has every information regarding the attestation type, the source ID, and the voting round. So the FDC verification contract on chain finds it easy to locate the specific macro root regarding your data because it has every information it needs. It has the macro proofs, then in the data, in the response data, it can get the voting ground and every other thing regarding the information, regarding the request that was made from which this data was derived. So you have the response data, and then but inside here you also have the request body and then the response body. So the data that has been brought on chain will be in the response body here, but the request body that you made, the body of the request that you sent to the FDC hub is also available. So you can actually review it as well. There's also a data structure here regarding the request body. So everything is here that you made. Because this is a Web2 JSON request, it has the URL, the HTTP methods, the headers. I'm sure you remember when we made the request, when we were preparing the request, we had all this information available. Then the response body is right here as an ABI encoded data. So then you can destructure this using the ABI decode method in Solidity, and we'll look at this. So this is the form in which the data is provided for you, but at the very surface, it's provided as a iweb2.json because we're working with web2 data.proof. So that's the external object. Then you can destructure it using the dot notation and the Solidity syntax as usual. So we've already extracted the data and the proof, and we're at the step of verifying and using the data on chain. So here, when we're passing in the data to the add character method, because this is now data that is coming from the FDC hub. So the FDC hub is practically off-chain in the sense that the only point of interaction between the network where you deploy the smart contract and the FDC hub is this point where you pass the data to a specific method on your smart contract. So this is the only point of contact between everything that happened with the FDC protocol and your smart contract, is that you pass in data that contains both the macro proofs and the data regarding the request that you made. So this is what we're passing. This is why we're passing this kind of data to the add character method on our smart contract. But it is coming from call data, which of course is passed through a transaction. If you're familiar with Solidity, I'm sure you know the difference between call data and memory and all those different storage locations. Okay, so after we're done with calling this method, then we wait for the transaction hash because that's actually a transaction we're passing to the contract that we deployed earlier in this function. So everything we've been talking about is done through the main function according to this template, and that is all that we had to do for us to be able to interact with the FDC protocol and then together with the smart contract that we just deployed. So for us to test this entire process like we've been talking about it, I hope my package is installed successfully. Oh yes, they did install. So I'm going to be using a different CLI interface. I'm not going to be working with this terminal in my VS Code. I'm going to be using this CMD CLI, but it's all in the same folder. So what I'm going to be running is running on exactly the same data. So no worries. So I want to clear this. And now what I'm going to do is run a script, run this script. So what am I going to do through this script? I'm going to prepare the attestation request. As you can see, I'm going to submit the attestation request, then retrieve the data and proof from the DL layer, and then deploy the smart contract that I want to interact with, and then interact with the smart contract. So those are the different steps. But if I want, I can actually choose to modify the smart contract. But let's see how it works, and I'll show you other things regarding the Systems Explorer, the Flare Systems Explorer. So since I used the package manager, I used this yarn. I'm going to type the keyword yarn. And since this is a hard hat project, next keyword will be yarn hard hat. Then I'm running a script. So this is how you run a script with hard hat. It's hard hat run. If it was Foundry, you would use a forge script. So my package manager is yarn, so yarn hard hat run. Then the script location. Where is my script? Scripts under scripts slash. So inside scripts, I have FDC example, then went to JSON.ts. FDC example. Web2 JSON.ts. So what network will I be deploying my smart contract on? Custom 2. Custom 2, yes. Okay, one thing I need to mention is that Hard Hat has configurations. So if you haven't worked with Hard Hat before you even specify the network, and before you specify the network, you need to have configured this network in your configurations, your Hard Hat configurations. Things specifically regarding the RPC that you're going to use, the RPC URL you will use, and then second, the externally owned account that will be signing the transaction, the deployment transactions and the interaction transactions. So I need to provide those two things. So when I look at custom here, it specifies the private key in my .env file, and then the RPC URLs are right here. So everything that I need to interact with a Flare custom 2 network is available to me in my configurations, even the chain IDs here. But I don't think I have a .env file, but I have an example.env file, so I can make a copy of it. I think I had it here somewhere. Contracts. Right here. So I want to make a copy of this because my project is designed to interact with a .env file, but I have the example. So how you make a copy of a file, cp.env.example, and the example I want to make an env file instead. Make a copy of it. What is it saying? Because it does not exist. Okay. I think I need to enter into this folder first. Yeah, so I have a .env file here. And then I want to pass the private key of the account that I'm going to be using to sign these transactions. So I think I have some custom 2 tokens on my MetaMask account here. So don't worry, I'm going to show you these private keys. These are just test accounts, but you shouldn't reveal your private keys if you're going to be deploying with an account that you actually store funds on. 48, okay. As you can see, it's actually called test recipient. It's just a test account. So if you work with the account that has funds, actual funds, I recommend you don't display it. It's very sensitive, and this is an issue I even have with Hard Hat itself, that inside the .env file, yes, it's offline, but it's inside VS Code, so all your extensions have access to all your files. I know you don't really upload it in the git ignore file, you actually remove it, but while you're still working in your VS Code, all your extensions have access to your files. So if there's a malicious extension, it's possible it could compromise your security. And this happened to someone actually. They used I think it was a Solidity linter or the Solidity code editor or something. I don't remember what it was. And that happened to them. The extension utilized the access to all their private keys and took everything from the account. So I recommend that even when you're deploying your smart contracts, try using something like an environment like that of Foundry. Maybe I'll actually do this again in Foundry so that you can see how private keys can be hidden away from even yourself while you're working with your applications. You don't actually see the private key. There's a way you can work with it and store it in a key store file so that it's safe and away from any person that might maliciously want to have access to your work, to your account. So specifically in this account, I want the private key. That was just something about developer security. So I just want to pick the private key of the account that I'm going to use to deploy my smart contracts. Okay, there's a warning here actually says don't share your private key. This key grants full control of your account for the associated chains. So if you haven't had experience with Web3 before, if you're just maybe joining this session for purposes of really learning about Web3, it's very critical that you keep these components safe and hidden from other people. Even though you actually see it here, this is just for my testing. I don't really store any funds on these accounts. But you need to keep these very carefully because they're private keys. They grant absolute access to your account. So yeah, the next step I'm going to do is paste this private key. I think this is all that I'm left with for me to be able to execute my script. So this is the private key of the account that I'm going to use to deploy. It's just for testing. And yeah, that's all I needed to do. Now, all I have to do right now is run this script, and it will execute everything in the main function as we have it in the script here. As we have it in the script here, it will execute the main function. As you can see, it's only the main function that I executed. And because it returns a promise, I used the then keyword and extracted the results of the entire process. Okay, so as our script is running, if someone has any questions, I know I've been talking for a very long time. I would love to clarify on some of the things that I've been talking about. So as this script runs, I'll be explaining some of the things that are happening. But yeah, any questions, please? I would love to have some feedback if we're making progress. Oh, it says it doesn't exist. I think I typed in. Yes, Teddy. Okay, so there was an error here because I didn't type the name correctly. So when I check the script name, it reads web2 json.ts, and what I entered here was different. It was WE without a B, so that's why it failed, and I'm running it again. Tracy, you had a question? Okay, as the script runs, I'll be explaining some of the things that are happening. Oh, it's okay, Tracy. So you don't have to worry about this tenderly configuration. It's just a glitch in the code itself, but the code works perfectly. So now what is happening in the background is that a request is being prepared. An attestation request is being prepared, and when it's going to be delivered, you will see the actual process because the attestation request will be printed here, and we'll see how the process went. So it takes a while, and remember, it takes up to 90 seconds for the entire process. So also, there are so many dependencies of the FDC protocol. So it had to compile 114 Solidity files. Those are quite a number of files. And when it's done, now we're moving forward. So I want to explain every step of the process. Anyone that is familiar with EVM standards, rather EVM versions. Okay, so before I even finish, so we have the request that was prepared here. You remember everything that we entered. So the response from the request verifier server is right there, and it is successful. So this is the ABI encoded request, and this is what is delivered to the FDC hub contract. And this is the submission request to the FDC hub contracts, and this is metadata about the round. You can see the voting epoch is 90 seconds, and the round ID is that. So we can actually see the process of verification happening on this link on the Systems Explorer. So we can actually tell when the round is actually done by just viewing it from here. So I want to show you what it actually looks like and explain some of the components. So we're making a Web2 JSON API request, and you can see the voting ground. That's the ID of the voting ground. These are some of the requests that were made within this round, and we should be able to see ours, a Web2 JSON request. I hope it's this one. There might have been another one, but there's a Web2 JSON request. So now the attesters are going through the process of sorting this information, seeing what they can verify and what they can't. And then what is going to be verified will be provided on chain through a Marco tree, through a Marco root. Then you can prove the authenticity, the integrity of this data using the Marco proofs that are going to be generated from the DA layer after the method where we pass the data to the DA layer. But as you can see, we're waiting for the round to finalize. And even when you look back here, the round hasn't finalized yet. See that? So this is the Systems Explorer. You can see the status of the process of verification, and so our data has gotten 99.98 signature weight, which is more than enough for us to access this data on chain. So what is required is that every single data point has at least 50% or more signature weight from the testers for it to be accepted on chain. If anything has less than that, if any request has less than that in the acceptance of validity from the different attesters, then it cannot be taken on chain. It has to be at least 50% or more. So I hope there are more requests within this round that are being attested. I want to see if there is any that has failed. So this round, all the requests I think were successful, but sometimes they do fail. You can actually see one that has a 0 point something. So that means that data is not accessible to you on chain. You will not be able to use it. You'd have to either make a different request or make some changes within your request that make it accessible, that will allow for the verifiers rather the attesters to verify your data. So I don't see any other Web2 API request here. These are requests for different attestation types. So I think the one that was actually on the very first page was ours. There was a Web2 JSON request here. So we can check this request and see certain things regarding it. Maybe we'll be able to verify if it's actually our request. So the request body is there. And it contains everything you need to know. Oh, there's a transaction hash here. I think we can verify through the transaction hash. So the transaction hash here has an E95. Let's see what the transaction hash on our request here reads. This is for the smart contract. So it's not for the request to the FDC hub. I'm looking for the request hash. The request hash should be somewhere. So yeah, I think you can see that this is actually the submission request that we have here, and is exactly the same that we're seeing for the Web2 JSON request in this round, the voting round that ends with 684. We can verify again, it's E957, even this is E957. Okay, so this is actually the request that we made and it was successful. So that we received the data went through the entire process, and I can go through it again for clarity. So we made a request, first of all, prepared a request, then an ABI encoded request was generated from the verifier server, and everything is right here in the script, as you will already go through it. So for you to understand this script, you must have knowledge of both Hard Hat and JavaScript. And I know there's a lot of things we've been going through, and that's why I really did the first session, for us to at least understand the entire context of how FDC operates, so that it's easier for us to, catch up on this session with some background knowledge. So we prepare the request using this method, prepare attestation request base, and I looked through it earlier on. So because of this, the bulk of all these concepts, I couldn't retype everything, but I hope my explanations made sense. So if you go back and review this code, it should be easier for you to understand. So I'm going to prepare um, another repository for the EVM transaction attestation type, for the payment attestation type, and yeah, I think I'll prepare for those two first. So that's easier for us to perhaps be able to create decentralized applications that utilize those attestation types in in our future hackathons, and perhaps even building our own projects on Flare. Okay, so we had this data, we submitted a request, and we got the response, and then we sent a request to the proof, to the DA layer, rather to the FDC hub contract. So we generated the proof. So this is the proof that actually our data is valid. And these are the proofs, the Markov proofs that have been generated from this attestation round. So this is part of the data that is provided to the smart contract that we deployed. And then these proofs are used to verify if this data is actually valid against the Markov root of the round in which it was created. And you remember when we looked at the interface itself, the iweb2.json.proof structure, it had a number of components. It had this section where we had the Markov proofs, and then also where we had the data. And the section of the data also had a number of things that would help the FDC verification contract to know which actual round to check for this data. There was a section for voting round, if you remember. When you look at the response data, look at the response here, you can even see the voting ground in which these Markov proofs were generated. So it's much easier for it to know which Markov root to check against these Markov proofs that have been provided to it in the smart contract. And that's how effective FDC is. And everything we needed to do has been done. So this is the ABI of the smart contract. Now moving forward, so that was just a part of the FDC, but then we also deployed a contract. If you remember, there was a section where we deployed a contract, and that is right here. I think the function is just above this. So we also deployed a contract and then provided the proof and the data from the DA layer to the smart contracts. And it's particularly the function we're providing that data to is this function add character. So we're providing the data in the form of iweb2 json.proof, which contains everything that is required for the get FDC verification contract to verify that actually these proofs are part of an actual Markov root that exists for a round that is already complete by the FDC protocol itself. Okay, so what happened was when we called this method add character, we added a character. So this is now the Solidity contract itself. We added a character, although I think it was added to a memory structure, so it wasn't really interacting with the state variable that was declared up here, Star Wars character. So this is the actual contract. This is the smart contract. And for us to actually verify if the transaction has happened, we're going to check the Question2 Explorer if actually this smart contract was interacted with, or if it was even deployed. So Star Wars contract character list v2. The very first thing that was done when this data was provided, it was taken through a verification process to verify if actually the proofs that were provided in that data are part of a Markov tree that already exists by checking them against the Markov root. Now, moving down here, I think this method is actually defined within this function, within this contract. It's down here. So it also takes in that data in that form and then does just one thing. So you call the get FDC verification. Now this is the function that actually verifies if a proof is part of a Markov tree that a Markov root that exists, which verifies that actually this data has gone through an attestation process and it's available for you to use on chain. So on the contract registry, which we simply import like we did with FTSO, so the contract registry contains all the contracts for the different protocols, for the different Flare protocols, either FTSO or FDC. You should be able to receive, to get all the contracts that are required, and why you should really use the contract registry. So first of all, to understand the purpose of Songbird, Songbird is the canary network. It's a test environment where protocol upgrades are done. So for instance, if there were certain changes that the Flare developer community wanted to change about FTS, or maybe how it delivers its data, or how FDC actually works, everything is first tested in the Songbird network, on the Songbird network. And now, when it's being brought on Flare, everything is provided. All the updates are provided through the contract registry. So if you hard code the register, these contracts, then you're going to have an issue in case these protocols are upgraded. Then your project will not be forward compatible. That simply means that you won't be able to access the new features that have been upgraded in the protocols. But everything is provided through the contract registry. If you're familiar with the proxy architecture of Solidity contracts, so even in Solidity, much as all the code is immutable, you can create a proxy and then an implementation contract, so that every time you make changes to the implementation contract and redeploy it, you give the proxy contract the new address to the implementation contract. So it always has the updated implementation. So that's the same thing that is happening here. You don't hard code contracts that you're going to use in this case, we're talking about the get FDC verification contract. You get them from the contract registry. It's much easier for you to, accommodate all the new features that might be added to these protocols later on. So that get FDC verification contract has so many other methods on top of it, inside it rather, that are responsible for verifying different attestation types. So this one specifically verifies Web2 data, and it's not verify JSON API, it's verify Web2 JSON. That's the actual method that verifies that the proofs that you provided are actually part of the Amako root that exists, which simply means the data has actually been attested and accepted to be used on chain. The data that has been provided along with these proofs. So this method simply provides the verification, and it's a Boolean value. It's either true or false. So it's the method that has actually been called up here in add character. So why it's actually been a separate method is that anytime you have different methods that are going to need this data, they have to first verify if the data is actually valid. Because if it hasn't been attested, then it's not available. That's simply it. While you might actually choose to bring that data, rather to access the objects on which that data is supposed to be defined, you won't have access to that data simply because the DA layer only contains data that has been attested by the FDC protocol itself. So it's only prudent that you first check if the data is actually valid by checking the validity of the proof before you can actually use the data. So that's what has been doing here. That's what was being done here. Then after you verify that, then you can start to destructure the object, the structure rather. It's a user-defined type struct. Here it was being accessed, and later on inside our script, we also call the get all characters function, and it returned all the data that was brought on chain. So if you're familiar with Solidity, I'm sure you know what's happening here. We're declaring an instance of an array of structure war character, which is actually a structure. It was actually defined here, or the Star Wars character. So it contains the name, the number of movies, the API UID, and the BMI. So everything that is going to be inside this array has to be of that type. It's going to be stored in memory, and the actual variable is called result. So creating a new one, a new instance of Star Wars character array, and then passing in the character IDs to know the length, of course, and then later on destructuring the characters, the characters array of structures that was declared up here as characters, then all the characters passed through the add character method to populate it. So I should be able to even see this result in the script. So it's actually here, the Star Wars characters result from the get characters method being called. This is the transaction hash added the transaction, rather where we added the characters to the contract that was deployed. And we're going to verify this. So first of all, let me copy this transaction hash and see it's part of a transaction, part of a contract that actually was deployed. So I'm going to check the Explorer. So if our contract was deployed, we expect it to be of a very specific name, the name of the contract that we have here, which is Star Wars character list v2. That should be the name of the contract that was deployed, because I think it was also verified. And how I know that? It's because I read this script also. So there's a verify method as well. After we deployed, it's here, deploy and verify contract. And that's what we're doing here. So if you're familiar with Hat, I'm sure you know what is happening here. So here I was creating a new instance of that contract, getting the compiled artifact, and then creating a contract using the compiled artifacts, then passing in the arguments. So precisely it was just deploying the contract. So I copy the transaction hash, and I'm going to check if this transaction hash is actually a part of a contract that exists, that has been deployed. And when we check it, yes, it actually does exist. So that's the transaction hash, and we interacted with the contracts, these contracts. Okay. We could actually look at this contract. When was it deployed, and how many transactions does it have? So it has 2 transactions, and when we check it, they should all coincide to the time when we deployed our contract just a few minutes ago. 2 transactions on this contract. So the contract wasn't verified. Okay, I'm just waiting for these transactions to load. Okay, we have 2 transactions here. One of them 17 minutes ago was a contract creation, and then the second is the actual contract call, and we were calling the add character contract function. So that tells us that the contract was actually deployed, and yes, we did call the method when we added those different characters after we got the data from the DL layer, and the results of the get characters method right here, get all characters method, the results were brought back here and printed in our script, through our script. So it's really that's what happened. So when we interacted with the contract, we got that information and deploy and verify, then we interacted with the contract. So 2 functions were actually called in this method. In this function, interact with contracts. The first was to deploy, to add characters through the add characters method. And then the second was to get all the characters, as you can see it here. And since it was interacting with an external execution environment, we had to await it to return a result first. That's how asynchronous processing works. That is essentially an example that shows us the entire process of how you can prepare data and get it from an API endpoint to actually having it on chain. So the real issue here is because it would have been very easy for us to just get this data and pass it through the smart contract, because we deploy the smart contract from here. This is an off-chain environment, so we simply deploy the contract and get the data from the endpoint, because it's a script, so that means it can interact with API endpoints. Even if I was using npm, I could actually simply get this data and bring it through the smart contract here, because I've deployed it here and I've interacted with it here. This is an off-chain environment. That means I can actually get data and just provide it through this environment. The issue is you cannot guarantee the integrity of this data. The security is questionable. The security of this data, the integrity of this data is questionable because what if the endpoint is hacked? What if the endpoint is hacked and then perhaps it was providing very, very sensitive data? We could say a data availability layer, like a dedicated data availability layer, somehow maybe has data that of things that haven't happened. So you're querying an endpoint, or maybe an indexer. You could be using an indexer, for instance, and somehow it has been hacked. Somehow it has been hacked, and you're getting that data and passing it through your smart contract in this off-chain environment, and then doing certain operations on chain based on this data. So you picked it from somewhere, a place whose credibility is still questionable because the process by which this data is made available from the source where you picked it is not very secure. So when you do that, somehow there's a possibility that sometimes if there's also a possibility that that data source could be hacked, then you could provide data that has been compromised on chain, which makes your smart contracts both insecure and vulnerable to a certain amount of attacks that I cannot even comprehend. But if it has to go through the FDC protocol, if it has to be verified by all the validators of that network, in this case Flare, which has enshrined data protocols, so all the validators are participating in verifying if actually this data is authentic, using a number of mechanisms like we have seen, although the process is a little bit more technical, but it really involves all of them participating in testing if this data is valid and authentic. That's the only process through which the data can be brought on chain and can be utilized on chain with the absolute guarantee and assurance that it has gone through a process of transparent verification of its integrity, of its availability. And I think that's a good thing because if we're going to be building decentralized applications that are dealing with people's money, applications that are dealing with very sensitive processes, then we need to at least be sure that the data that we're having access to is coming from a point where we can have the confidence in the source of the data and the process through which it was provided to us. Yeah, that's essentially about FDC. Though we've done just a little bit, we went through this workflow step by step, like you've been seeing, and the kind of data that we've been providing is Web2 data, but there are so many other data attestation types that we can prepare, and I am going to specifically create one for EVM transactions and another for payments on XRP, so that it's easier for us to recreate this process for the different attestation types, because there are slightly different components, specifically in the request body, even the response object, that are different for these different attestation types. So it will be very helpful that we have something that is simpler for us to use. So I hope this session was helpful and you can build applications using the knowledge that we've learned today. And finally, before we close, there's a specific bounty that has been put in place for you to build something with FDC. And if you're in session and you know someone that might be able to build with FDC and they probably already left the session or they haven't attended this session, you can let them know there's going to be a bounty for this session if you can build something with FDC. The details of this bounty will be communicated in the forums. I will communicate this in the Flare Africa Telegram channel, specifically in the developer topic. So keep an eye there for information about this bounty. And yeah, I think that is it for this session. Unless someone has a question, I would love to close it here. Okay. So maybe the other thing I would love to talk about is that if you haven't filled this form, the Flare Africa Sprint Bootcamp Session 4 feedback form, please do fill it and you can type your name here and X handle so that we can follow each other later on. And also the links to the session, to the things that the different platforms I looked at in this session are right here, so you can always come back to this page and access them. I think I should actually put this in the forum. So since we have no questions, I would love to close it here and have a wonderful evening and a wonderful weekend.